Okay, Assalamualaikum and good evening, good morning.
Yeah, morning, doctor.
Okay.
Alaikum salam. Good morning.
Alaikum assalam wa rahmatullah.
Okay, so we
Waalaikumsalam.
continue our tutorial here. So I think I can go a little bit faster. So because a few questions here, it might be just the warming up question as you want. Okay.
Take your time, Doctor.
Okay. Yes.
Sorry for interruption, but do you remember when I sent you on WhatsApp about the result of derivation?
Result of vibration.
Derivation.
Derivation. Yes.
Yes, I'm just trying. I just remember it, and I want to talk with you about it because the result is different.
Oh, the your derivation about continuity equation.
Yeah, right.
Okay, later on I will know.
Okay.
Okay.
then.
So because I think you make mistake in term of partial derivation, that's all. And then might be we could simplify it. We could assume it is certain terms is equal to 0.
Mhm.
Okay, that's all. Okay, I will check it later on.
Okay.
Okay. Okay. So this is just a question from the textbook. So 1.8 here. So we have we need to calculate the strain rates for epsilon RR and epsilon R naught here. And then we need to calculate the required particle to move from the point of 2R and pi to the stagnation point. So and then so I just we in previous notes we know that from the basic of flow around cylinder, so we could get the value of UR and U theta here. So I show you the derivation of this one, and to get the strain rate of epsilon RR and epsilon R naught here. Okay, so you could get from the textbooks. Okay, I also give in my website, so I upload a few notes about this. Okay, so okay, this is the important one is this one. Okay, that we want to know if the R is equal to R. So we substitute in the UR equation. We found the value is equal to 0. So why? Because okay, so if we have the component velocity of R here, so the flow will not exactly flow around the cylinder. So it will flow around like this. Okay, because it has element of velocity move outside the radius. Okay, so so if we substitute the value of U theta here, so we will get the value of negative 2U sine theta. So the theta here means the velocity that's flow tangential to the surface. So and then if we substitute, okay, so this is to calculate the ER here, the epsilon in term of RR and in term of E theta here. So so the basic idea is to make sure that you could derive it very well. You do the differentiate this very well. Because in some in textbook they will write you something that DUR over DR here. So then when you do in your hand writing, you do the differential. So please write as D over dr and then UR. So mean you differentiate the term of this velocity into the term of R. Okay, so and then you will get this value. You substitute the coordinates here, and then you will get the answer. Okay. So and then so this is all the answer from the equation is from the textbook. You substitute the value, so you will get the value. So and then for this one, okay, the time required for a particle to move from point 2r pi to the stagnation point. So here, so the idea is if we have a cylinder here, so the coordinate of 2r pi is, So pi means the location. So we have the angle of here, and the location is 2r. So r, so in this coordinate, so you will have r and theta. So means we start 0 is here, and you pi means somewhere at this area, and 2r means the location is actually 2. It's actually 2 times bigger from its radius. So the find here, and we want to calculate the time required for a particle to this for a particle to move from 2r pi to the stagnation point. So let's say if the flow is from left to right, so we know that the stagnation point is here and here. So means that what is the time for this particle to move until it reach the stagnation point here or at here. So we calculate this one. So we have a ur is equal u1 over r square cos theta like this, and then we substitute the angle is -1. Okay, so and then we could have this one, and then we could say that from the Cauchy-Riemann equation, or the equation of velocity here, so it can be written it is equal to dr dt, because we want to find the velocity or the time. Okay, so and then we bring the dt to the left hand side. So and then we bring something with the terms of r to the right hand side, because we have the r here. So we integrate, and then we substitute the value of r and to r, because we have a location of 2r here, and the stagnation point is occur at r. Okay, this is 2r, and then we found that it is equal to minus infinity. So and then the answer that we could get is actually it cannot reach the stagnation point. So this is what we have here. But what I want to tell you is, again, please understand that in master level, sometimes your answer in mathematics is might be you need to interpret your answer in from your calculation to suit with the application. For example, sometimes you have a something over something here, and then might be you assume that the value of the bottom one is equal to 0. And according to the mathematics, if you have a 0 over something, so you will have 0. Then that is clear, you put 0 your equation. But sometimes if you have a something over something here, and you have a 0 at the bottom readings here, so you will need the infinity. Okay, in some calculation you may take this term is actually not exist. So mean not exist means you could take it out from the equation. So now your equation can be solved, because you don't have any terms that give you a 0 or infinity. Okay, in this situation, so in this calculation you will get infinity, means that, okay, it is not because it is too long, because you cannot say that it is an infinity time, because it takes too long to get the molecule at 2r to reach the r location. No, that is not the meaning. The meaning of this infinity is it is no possibility. There is no possibility of molecule at location of 2r to reach the r, because the basic idea is every flow here, okay, will flow on its own location, on its own path line, so it will not cross each other. So means that the line that create stagnation point here is actually the streamline at the middle. So, okay, so means that the location here is, when we have this one, so it will flow outside, because the line here is actually fixed. This the idea of infinity. Okay, so and then for question 1.9, for example, so a commonly used equation for state for water is approximately independent of this one. So we have this equation from the textbooks, and then we need to calculate the pressure ATM here required to double the density of water, the bulk modulus of water at 1 ATM, and the speed of sound in water at 1 ATM. So okay, so this equation is from your textbooks. So means, okay, for the A here, we need to double the density. So we have P equal to P naught. So and then we substitute the value. So we have the A is equal to 3000, depend on this from the textbook. So it is the coefficient for this calculation. So we have the N is 7 and so on. So we get 300,000 ATM. So this is the meaning is, so it is not about the calculation of this one, but what I want to tell you is we are now calculated about water, and water the means that water is very hot, so it's not compressible, so it is totally incompressible. That's why if we want to double the density here, so the meaning of double the density is to compress the water, so we need to compress it twice. So the answer is it is impossible. Okay, so another idea here is in your calculation later on, especially when you do research, is sometimes when you need when you do research, okay, might be you could calculate its possibility in mathematics. So you get a 381,000 ATM to compress double the density. But I hope you could think about the logic of your work, okay, or the process that include in your work. So in this mathematical calculation, if we could supply 380,000 ATM, we could double the density of water. But the idea is actually it is impossible to compress the water, because last time we have a little bit upset in term of in master research. For example, students propose to have to increase the surface area of nanoparticle. Okay, you could imagine that we have a nanoparticle, a particle in nano size. So they do the calculation using simulation. So they could say that to uh, to to increase the area of nanoparticle is by having a golf ball pattern on the nanoparticle. So they start to have a golf ball pattern on nanoparticle. They calculate everything precisely in simulation and so on and so forth. So they will get a new curve. They will get a result in terms of numbers like this and so on and so forth. And the conclusion is, if the surface, the golf surface, mean the texture surface on the nanoparticle is good to enhance the heat transfer and so on and so forth, according to the equation and so on and so forth. But the first question and the last question for that research is how to fabricate this one, because nanoparticle is around 9 nanometer. The particle diameter is 9 nanometer, so means you need to have a drill bit here is around 2 nanometer. So which machine could drill this hole? So the students say, oh, it's not my scope, I don't know about that. What I know is if I could put the texture surface on nanoparticle, we could increase the heat transfer. So I think please relate to the real situation by understanding the numbers here. So and then for the next calculation is to calculate the pressure and so on. So and then we have a bulk modulus. Okay, so we have a volume here. So we have a dp, the volume. So and then we could substitute into the equation. So finally you could get the value here, dp d rho is equal to 21.04. So and then we could calculate the k. So it is equal to 21,000 atm. So this is in term of kilopascal. So and the speed of sound, so it's depend from the textbook we get the C here, the speed of sound in water, so it is K over rho naught. So we substitute the value in the textbook, so we get it is 1,460 meter per second, the speed of sound in water. Okay, so 1 to 8 is quite to just a warming up to use the common equation from the textbook, and this is the main idea for the fluid properties. Because as I said, in fluid, okay, so it is common with other parameters. We could conclude that there are three basic terms that you should know. One is the density, and then you have the specific gravity and also the specific weight. So it is equal to gamma here. So, and these properties is actually occur at all the element. So whether it is gas, fluid, liquid or solid. But another property which is the viscosity. Okay, and the viscosity is only occur for the liquid. Okay, so and then one of the common application that using the viscosity here is something like this. So we have a sliding plane like this. So and then we have a cube with certain weight. So and then we give them a thickness of liquid here. So normally we will use an oil here to create a thickness, a gap between this object and this plane. And then for example, we have a 30-degree angle here, so to make sure it could slide naturally with the gravitational force. So in this question, we need to calculate what is the terminal velocity. So the terminal velocity is, the idea is when you have this situation, so you will find that the object here will slide down. Okay, in the first it's not a fully developed condition, so the velocity is start to increase and increase and increase, means the increment of velocity will create acceleration, and then at certain time it will give you a constant velocity. So the constant velocity is called the terminal sliding velocity. So normally, so it will take a longer plane, a longer distance to take the terminal velocity. So and then we need to calculate what is the time required for the plate to accelerate from rest to the 99% of the terminal velocity. So means that it's before it reached the terminal velocity. So this situation is actually occur regarding to the viscosity of the fluid.
Velocity occurs when the acceleration is maximum. Can I say that?
No. Terminal velocity means, okay, you just imagine you have an object sliding, so it's become faster and faster. But after certain time, so there are no increment of velocity. It will slide at constant velocity. Means the zero velocity is, it will slide with constant velocity, means the acceleration is zero.
Okay.
Okay. So, okay, it's something like when you free jump for parachuting, for example. Okay, the gravity will pull you. Okay, in the beginning you will feel that you are become faster and faster falling down, but after certain height you will falling down at constant velocity. That is the terminal velocity actually.
Okay, thank you.
Okay, so this is the situation. Okay, so first about the sliding velocity here. So we assume that the sliding velocity, so we have this one, so we have the box here. So the sliding velocity, so you have the weight here. So and then because we have a viscosity between these two planes, so we assume that the shear stress, so we have the tau here, the shear stress will give you a resistance. So and then because we have an area here, so we've assumed that we have another resistance from bottom to the top like this in this direction to which give you resistance which is tau times A. So because the force is equal tau times A. Okay, and then the weight here will pull this object downward, but because we want to solve equation, we want to solve something about force, so you need to solve it according to its axis. So because the shear stress is occur at this direction and this weight can be divided into this direction, so we say that this is W sine theta. Okay, I know. I hope you could know the to get this one. So because we have angle here, okay. So and then it is equal to here, okay. So and then so we equalize this one. So we have the W sine theta is equal to tau A, and we substitute the value of tau with mu du dy. So we have this one. Okay. So and then we assume that the du and dy here, so it looks like the differential terms, but in this situation we could assume this is about the u here is the difference of velocity, and dy here is actually the difference of y-axis. So the difference of y-axis is reflect the oil thickness, and the du here is actually will be the terminal velocity, because we assume that there are no the velocity is now constant, so means that if we stick with the idea of du2 minus u1, you will get 0. So but it doesn't mean that your equation will become 0. So the mathematics is yes, might be 0 because there are no changes in velocity, but we replace that term because that situation is called as a terminal velocity. So and then we have this equation. So and then we could get that the terminal velocity is 0.245 meter per second. So it means that when the box is reached 0.245 meter per second, so the velocity will not increase anymore.
Doctor, excuse me.
Yeah.
Terminal side velocity, it means no change in velocity, right?
Yes.
Okay.
Okay. Okay, so for the B, so it is a time required for the plate to accelerate from rest to 99% of the terminal velocity. So the word 99% is actually to reflect the moment it's reached this terminal velocity, means it's become the acceleration, it's become higher and higher, and suddenly when it's just before it's become 0 or something like that. Okay, because we will have another term of 99% when we try to define the boundary layer in chapter 4, 5, and 6 later on. Okay, so the equation now is actually, okay, we assume that it's 99% of terminal velocity is at the edge of the total force that equal to the second law of Newton. So F equal to ma. So and then we have this one. We could assume that weight W sine theta minus tau A here. Okay, so it is equal to total force. So it is equal to ma. So and then we know that the angle is 30 degrees, 30 degree. So we could replace the sine theta with 0.5. So tau is mu du dy, and dA is the area of the connected for the area that make contact with the lubricants, with the oil. And ma here is the acceleration here can be replaced with dv dt, and the m here can be replaced with weight times g, because we have weight is equal to mg. So and then we replace mass is equal to weight divided by g. Okay. So and then we rearrange this one. So because we need to calculate the time here. So this is the time. Okay, we bring to the left hand side to, and then we could simplify our term like this. Okay, and then we could simplify our term like this. So this is velocity. Okay, we have mu. Okay, so and then we could rearrange our calculation. Okay, this one. So we cannot get finally the dt here. So and then because we have a dv dt is equal 0.5 g minus mu ag omega wy and v here. So it is a little bit okay. So now to make our calculation easier, normally people will bring this one to the left hand side and we start our calculation with this one. Okay, so we have dv over dt plus mu ag w y v. So this is the velocity. Okay, so and then 0.5 g. Okay, so in many textbooks they will solve this one with the idea of integration factor. So the integration factor is we try to start our calculation, or we need to rearrange our terms by using these terms. So epsilon, epsilon is not exponent, exponent by the power of integral of p times dx. So so how we could do this? So first we assume that we have velocity here. So we assume that the terms except of velocity is equal of p. So and then we substitute in this idea. So we have the integration factor exponent by the power of integral p dx. So we substitute the mu ag w y like this, and then we integral in term of time dt here. Okay, so we have the okay, because we want to get the dt, so we have the we replace the dx here with dt, so we get the exponent by the power of mu agt over wy. So and then we substitute the value here. Okay, we substitute the value here with so we get, means here we get the integration factor is equal of this term. So what we need to do is we multiply both sides with the integration factor. So we have this like this, and we have this like this, and we have this like this. So why we need to do this? Because because we have the basic rule of this one. If not, we are not capable to simplify these terms to get the value of v, because we have the dv dt at this side. So we have this one. If you see the rule here, so we have d dx e by the power of x squared times y, and so on and so forth. So it can be solved like this one, because it is, you could have you could see the similarity here. So and then from equation 1, so from these basic rules, so it is equal to d dt v times e by this power and equal of this one. And then now we bring the dt to the right hand side. So we bring it here. So we integrate both sides, so we could get this term. So and then to make it easier, so we could divide left and right hand side term with the e here with the exponent. So finally you will get the value of this one. However, we still have the value of c. Okay, so c is the constant, so we need to calculate the constant using its own within its boundary condition. So we put to make it simple, we say it's that the velocity is 0 at the time of 0. So we substitute the value of t0 and v0, at this situation, so we will get that the C is actually of this equation. So we have the negative of this one. So and then, so again here, so we assume that the y is cannot be 0 because y is the film thickness. You know that normally we have tau is du mu du dy. So the y here is actually reflect the gap. So the in this term, in this problem, so we assume that y is not equal to 0. So then we substitute the value of c. So we have this term. Okay, so and then from part A, where we could have the equation of terminal velocity. So we substitute the mark here is V star. So we could rearrange and we could have this one. So and then if we substitute to the equation, so we could rearrange the equation into equation of 6 like this. And then we says that we need to get the time 99% before it reach the terminal velocity. So we just give an idea of velocity is 99% of terminal velocity, and the time will become t star. So this is just the way we solve this one. So we substitute this one, we solve all these equation. So finally we could get this one. That's why if you find in internet and so on and so forth, the equation to calculate the terminal velocity is actually this equation. So it simplifies from the idea of integration factor. So if you substitute all the values, so you will find that it is 0.23 seconds before it reach the before it starts the terminal velocity, because the 99% is actually just to reflect the starting point of the velocity, the terminal velocity. Okay, so for question 1.11 here, it is actually to just to remind us how to deal with the gas, because I think it's that okay, so from 1.13 here, 1.11, so we have gas nitrogen. Okay, wait a minute. Okay, nitrogen here, so it gives at 86 megapascal, and the temperature is 49 degree, and then we need to compare with the measured value of 45 micropascal second. So here is, if we have a nitrogen here and 2 here, so we get the all the things here. So this is the parameter, and this is actually the common fluid for the critical point constant for common fluid. So the idea is this is the representative value that you could use in common solution. Okay, so and then we know the temperature. So from the table, the critical temperature from nitrogen is 22 degree R Rankine. Okay, so and then we have the critical pressure 33.5, and this is the critical viscosity. So we need to convert the Rankine unit to Kelvin. So we have this term. So this is the equation. So you just time with 5/9. So and then we could calculate the reduced temperature. So it is we have 49 here. So we plus with the we convert into the Kelvin, 273. So we divide into the critical temperature. So we have 2.553 Kelvin. So and then from the ATM units, so we need to convert to Pascal. So it is the common one. ATM is actually the pressure of the ATM pressure right now. So it is around 101.3 kilopascal. So we write 101,325 Pascal. So we time with 35.5. So we get the answer. And then we could calculate the reduced pressure by using this idea. So we have the common pressure divide by the critical pressure in ATM. So the reduced pressure ratio is 25.336. So and then by using this table, so we could assume the reduced viscosity by using the figure of 1.7 of this one. Okay, so here, so the idea is we have the 25, I think. So this is the, so TR is 2.5, so might be it is around here. So and then the PR PR is 25, so we have the PR the 25 here, and then if we get the value, it is around might be 2.5. Okay, so and then we could calculate this one. So we just take 2.5 here, so and then we have the dynamic viscosity, and we could calculated the dynamic viscosity of 45 micropascal per second. So here, actually, the question here asks us to, if you want to calculate very specific, according to the situation that you do your research. So you need to understand, or you need to know the way how to get that one. Okay, and another idea about this chart is, so normally all the estimation of so many condition of gas, especially gas, because in our previous calculation we assume that liquid, for example water, is not easy to be compressed, so the value of viscosity, the value of density, and so on is quite constant. It's okay for you to use the common one. Okay, but the gas, they are very fragile. They can be compressed. They can change their properties easily. But actually, previous researcher has plotted all the value in a graph. Okay, what you need to do is you need to find a chart like this. So not necessarily this chart, but the idea of this question is, that's why when you do research, you need to take books of the handbook of fluid mechanics. That might be a good book for you to refer any calculation or any chart that built by previous researcher. So from that chart in handbook, they will give you a few explanation about equation, and then they will give you equation. So but they will give you chart, but at least you need to know how to calculate or how to read the x and the y axis, and finally you could get the value that what you want. Okay, this is just the example, not okay, this is not for the final exam, don't worry. Okay, so this is by the to idea of how, because when you do research, especially in your master project, okay, please refer textbook about the handbook of fluid mechanics. They will give you a lot of chart, so I think you have experience when you solve problems in your works every day. So you are not calculating one by one, so you will see chart, you will see the x-axis, and then you will go for the y-axis to get the value that you are desire of. Okay, and then this is about the another thing, means the thermal conductivity. So for example, you have at 400 degree Celsius, you have 1 atm, and then you need to compare with the measured value of 0.05015 watt mk millikelvin. Okay, so here actually I would like, okay, so here if you see this one, for example, you have the thermal conductivity at 400 degrees Celsius. So you have the 400 degrees Celsius here. So you have all the parameter here. Okay, so maybe you could refer to the table A5. So the TC is actually 238. So the critical temperature, you have the temperature from the question is 400 degrees Celsius. You convert into the Kelvin. So you find that the T, according to the condition, is T is larger to the critical condition. So we could calculate this one by using this equation. So this is
Doctor,
yes,
sorry for interruption.
yes,
Critical temperature from the table.
yes.
Okay.
Okay.
We should-
Okay, so this is the equation. You just substitute everything in the equation, and the n here is actually is the constant. So it's in this situation it is equal to 0.8 0.81. So it's refer for the air. Okay, again here, okay, it is just for your knowledge. So the air is the combination of a few gases. You have carbon dioxide, oxygen, argon gas, and so on and so forth. So sometimes air, not sometimes, all the time, air will give you a specific value. So if you have air, so please make sure that you refer to the chart of air. Okay, because the single gas, for example, oxygen, nitrogen, and so on, they will carry another values. Okay, so you substitute in the value, so you will find K is around 0.005015. And if you compare with the calculated one, so it might be the error is 0.2%. So why? Because for the measurable, for the table, the way they are developed, their table is actually based on the experimental and also for the calculation. Because sometimes they will we still, I personally would like to say that we still don't know what actually happened when we increase the temperature of certain gases, because the prediction of the molecular movement is just a prediction. Okay, so this is a very important topics. Okay, because okay, in last 2 or 3 questions is actually there. I would like to hint you that, so for gases, okay, you need to very carefully. You need to very careful, because slightly increase of temperature and so on and so forth will give you changes in their density, viscosity, and so on and so forth. So here, okay, again with the gas mixture, because as I said previously, for the single gas, for example, for nitrogen, for air, and so on and so forth, even though you will have a very critical condition, for example, you want to make experiment in high temperature, in high pressure, and so on and so forth, normally they will a handbook, or there will be a chart for you to get those value, because they are a single gas. And for 200, I think almost 300 years, scientists from Western do this. So you will have the flow chart, no flow chart, you have a chart to get all those value in any condition. Okay, for 1.13, so it is very critical, because this is the way we calculate the viscosity and thermal conductivity. Okay, we estimate the viscosity and the thermal conductivity for mixture of gas. So this is very critical. Why? Because viscosity for gas is actually not easy to measure. It is different with the viscosity of liquid. So for example, you have liquid A, you have oil A plus oil B plus oil C. The viscosity and thermal conductivity of that mixture fluid is not critical, because it can be easily measured, the viscosity and the thermal conductivity. But the reason is simple, because the liquid is not evaporate. You can put a liquid in a beaker and you could measure it, and your problem is solved. So that's why if you see the trend of this question in chapter 1, they are dealing with gas so much, because gas is fluid, but you need to deal it carefully because it's fragile. The properties of gas, it can be changed easily. Okay, so 1.13, we are going to have a mixture of gas. So for example, we have a 23% of oxygen, of carbon dioxide. So we have 14% of oxygen, and we have 93% of nitrogen. So we have the 1 atm, and we have also the 20 degrees Celsius. So estimate the viscosity and the thermal conductivity of this mixture. So the viscosity here is actually can lead us to the idea of density. So means that we will know the viscosity, so we could estimate its density by that. Okay. Okay. So and then so this table, okay, is actually the value of mu for each single gas. So we have the carbon dioxide. Okay, the molecular mass is 44, oxygen is 32, and nitrogen is 28. So this is the mole fraction. So mean the percentage of this one. So and then we have the their own dynamic viscosity, and this is the thermal conductivity for each gases. Right. Okay. So the way for us to calculate the viscosity here is by using the equation of 1.54. Okay, so we have the idea of this one. So we have a mu mix, and we have a sigma sign of this one. So the sigma means the summation, the sum of for each value. But we have a phi here, the xj phi ij here. So the equation for xj phi ij is actually of this one. So this is the equation of phi ij, this one. And then here the m is the molecular weight, and the xi here is the mole fraction. So what we need to do is, first we need to solve the idea of phi ij here, and then we substitute in this equation, and then finally we could get the viscosity for that mixture. Okay, so first we develop a table. Okay, you just make a row here. Let's say this is the row of j, and you make a column here, and then you make this is the column of I. So and then let's say you start with a carbon dioxide is number 1, number 2 is oxygen, and number 3 is nitrogen. So you have also the same numbers. Okay, so carbon dioxide 1, oxygen is 2, and nitrogen is 3. And then we need to fulfill the value of phi. So we have a phi 1 means, so we have the coordinate here. So this is the calculation of phi between this and this. And 2 means it's from here to here, and 3 is from here to here. Okay, so how to calculate this one is, okay, so this is the example of the calculation of phi. So you just understand that the 1 here is the coordinates of the so this is the ij. So the first term is I, and the second term is the j. So mean 2 mean gas number 2 at column I, and number 1 at column J. Okay, something like that. So I think you already know about this. You know how to solve this. So you have a mu I and mu J. So we substitute all the values. So we have the molecular of J here, molecular weight of I. You substitute everything. So you will have that phi 1 is equal to 1, because the ratio between themselves. So the value is equal to 1. So and then if you go for the phi 1,2 here, so you are comparing the oxygen, I think. Like let's say, okay, you are comparing the carbon dioxide, okay, because it is a I here, so and then the J is the oxygen, 32. So if you solve this problem, so you will get it is 0.72. So for Phi13, so you have this value, so you are comparing carbon dioxide with the nitrogen, I think. So and then you will get 0.7234. So and then you write all of this value in this table. So you have 0.7269 and 0.272 7234. Okay, we are solving 1, 3, 1, 2, and 1, 1. So this is the value of 1, 2, 1, 1, 1, 2, and 1, 3. Okay, so and then what we do is we need to complete all this value by using the same calculation. So I just simply simplify them. So I just show you the calculation of this one. Okay, so and then you will get, again, you need to understand this equation, because this equation is, you need to calculate the phi, and then you need to calculate the sigma of x times phi. So now you are calculating the bottom part. Okay, so we get the phi here. So we need to multiply the phi here with the xj. So and then the sigma here can be written as this one. So and then we substitute the x here, you know. So previously we say that the x is the mole fraction. The mole fraction means the percentage of that gas. So we have 23, 14, and 63%. So and then we could calculate it. It is equal of 0.7876. So this is for the one row with for the 1, 1, 1, 2, and 1, 3. So and then you need to do this one again for the 2, 1, 2, 2, and 2, 3. So you get another value here, and then you will get for the 3, 1, 3, 2, and 3, 3. So get to any you will get another value here. So now we have a 3 value. So we have this, actually these numbers. Okay, this the matrix. Okay, what we know, what we want to use is, we cannot, okay, this value is actually related to the our last calculation. So the equation is to get the lambda here, means sorry, to get the sigma, the summation of all value of this one, x1 i1 for the term. So what we need to do is, so this is the I for the x and the mu for the first element, so which is the carbon dioxide. So we divide into the first item, because the first item here 7876 is actually about this one. So we are using the row of 1, 1, 1, 1, 2, and 1, 3. So we have 7876. We substitute here. So the symbol of sigma means you need to add all the value here. So you add all the value here. So you will find that the viscosity of that mix is equal to 1.608 times 10 by the power of minus 5 Pascal second. So the value is quite small, it's very small, because we are dealing with gas. Okay, you just imagine that. Okay, so and then we could calculate the conductivity here by doing the same things, but the equation for the conductivity is shown like this. So you are not using the same equation. So the conductivity is like this one. So you just, again, we start to calculate the value of phi ij. So you have the table like this. So you fulfill all the value here. And then we could estimate the value of conductivity for the gas mixture as this one. Okay, so this is a very important, because the mixture of gas is depend on the researcher. Okay, so as I said previously, for any condition for all single gas is actually can be found. Okay, the way is not from the textbook. okay, please don't find that graph from the fluid mechanic textbook, because they will not give you that there. Okay, please find fluid mechanics handbook. So because in handbook they will give you a lot of chart, okay, a lot of chart, a lot of graph with from the common condition to the extreme one. Okay. Okay, then this
Dr.
okay.
Ablis,
Yes.
this problem is very complicated. Its idea and mathematically mathematical solution is very complicated.
Yeah, this is chapter 1.
Dr.
No, 113, sorry.
Yes.
It's very complicated.
It's okay, you still time to understand. Yes, it's okay for
I
question
don't think so.
1 to 10 is very easy for you. Now we are going to the a little bit complicated question.
Doctor,
Yes.
sorry, for the equation,
Yes.
thermal conductivity and viscosity.
Yeah.
For the equation, you will give it to us, or we should memorize it.
So actually I will give it to you.
You will give it to
Yes,
us.
the equation will be give, but the way you solve is not
Okay.
given.
Yes.
Okay.
Of course.
Okay, the book you mentioned, the handbook of fluid mechanics, is written by who?
Oh, if you go to library, you could get a lot of fluid mechanic handbooks. So it's some kind of textbooks, but it's not for common student.
Oh, okay.
Fluid mechanic is the textbooks might be used for master by taught course and also for the undergraduate. But for the fluid handbook, it's actually for the researcher. It's actually the compilation of so many charts depend on certain area.
Would you please suggest one to recommend?
Okay, I will find.
I have actually, sorry for interruption. I have
Yeah.
two, and I will send them to all my friends.
Okay. You send what to your friend?
I have two books
Okay.
related to viscosity and fluid viscosity, and I will send them to all my friends.
Okay. Thank you very much.
You're welcome.
Okay, so sometimes now library UTM is all can I think you can search all the books from the catalog of the library online. So plus please try to find the fluid mechanics handbook, but please do not assume that when you get one handbook, everything that you want is on that in that handbook. It depends, because sometimes that handbook might be refer to the liquid or refer to the flow in pipe and so on and so forth. But there are two types of books actually. For engineers, for practice engineers, engineers want to solve problem in real situation, they will find handbook, not a textbook. Okay, for student, if they want to know how it's developed, the history a little bit, the starting, the main concept, and so on and so forth, might be they need to go for the textbook. Okay, that's the hint.
Can you recommend one, Doctor?
Okay, I will find it, but it's depend on the application that you want to go. Okay, I will find one. I try to
Give us the name, and we will search for it.
Okay.
Thank you, Doctor.
Okay. Okay, so in this question, so we have the 1.14. So it is again about the ammonia. So it is value of viscosity of ammonia gas depends on the temperature here. So you will have temperature and you have value. So if you search in internet, there is a method to calculate the viscosity of gas, the single gas, because we have an ammonia here. So ammonia, if you see the chemical symbol, so it might be the NH3O and something like this, combination of nitrogen, hydrogen, and so on and so forth. But ammonia gas is quite common. Okay, let's say this is a one single gas. So if you find in internet, you could find, let's say it's the Google is the fastest. So if you Google it, so you will find there is a device actually to measure the viscosity of gas. Okay, so it's using the idea. There is a lot of method. One of them is we just put we put the gas, okay, in control temperature inside a tube like this, and then we'll have a small object here. Normally it is a cylinder, okay, and then we make it horizontal like this, and we measure its the time or the condition, the object falling down here. Okay, and then we use the time to estimate the viscosity. Why? Because the gas is actually resist the object here, so means that you need to do something with the weight here, but at the same time the gas will flow into this gap, okay, slowly, and this will make this object will falling down at certain speed and at certain force. Okay, so and then by using this idea, we could estimate what is the viscosity of this of certain gases. As you know, we learned previously, we have, so from here, if we enlarge this area, so we found that, so this is the cylinder, so and this is the gap of the capillary tube, for example. So this is fixed, not moving, and this is the moving area. So we could have the velocity distribution like this. So means that we could have tau mu du dy. So by this idea, we could estimate the viscosity of this one. Okay, please try to find how to measure viscosity of gas. Okay, but in this question, okay, I would like to bring you that the way, because you are masters, so might be you need to do research and so on and so forth with something that really unknown. Okay, what you could do is you could depends on your graph. Okay, so for example, so this is the measured value of viscosity. So you will have a certain value of this one. So and then we have an equation to estimate the changes of viscosity and temperature. So we have this one. So what we need to do is actually we need to determine the value of n here. So and then it was given from the in certain textbook, they will give you a few numbers here for certain gas. Okay, but this question is, the idea is how the numbers is come from. So let's say we have an n here, the unknown value of n here. So and then we take the T naught is 300 degrees Celsius. So the T naught here is actually, normally people will take the room temperature. It can be, or we use the 0 degrees Celsius, 270 Kelvin, and so on and so forth. But the idea is the T naught is actually will become your reference point. So it's depend in here. So let's say we have, we take this value is the reference point. So we take T equal 300 Kelvin is a T naught. So we could fulfill this equation. We can calculate, and then what we do is actually we plot a graph. Okay, so let's say we plot a graph here. Okay, and then what I want to say here is, might be you will have the graph of this one. So you could make a log as and y-axis, and you will a log as an x-axis, and then you could plot it, and the end here is actually the gradient. So if you plot this graph, you will have this straight line, okay, almost straight line, and then you will take the gradient here is the value of n according to this equation. So now your equation is actually to become like this one with the power of 1.0451. Okay, this is what I would like to share here is, so when you do your master project and so on and so forth, so please try to plot your graph and so on. And then the tricks, okay, the tricks normally that a researcher use is, please do not plot your graph in usual terms. For example, you have a mu here and so on. Please try to use the idea of log and log, like this one. Okay, because the log and log here will help you to create curved graph into a straight line, to a linear graph. And then you could find the gradient as the exponential power there. Okay, you could estimate the value of n here by estimate the gradient of the log graph.